If you have questions regarding the exam, please take a look at the key that was posted to our Canvas page. We'll start there. Then you know what I was looking for. And if you're still confused, come talk to me. I'm more than willing to discuss the exam grades with you. Overall, I was pretty happy. Exam average went up. Unfortunately for me, majority of grades did not go up with it. Most of you maintained your grade, had the same grade you had before the exam. But they didn't go up, despite the exam average went up. So we can do this. We can do this. We'll get there. Hey, let's keep going. Meanwhile, I want to continue discussing powers and expansions and integer representations with this idea of modular exponentiation. So one of the important calculations we do in encryption is to take some number, raise it to a very large power, and then take the result mod some number m. Now the question is, how do I do this in an efficient fashion? And the answer is, it's actually most efficient if I use the binary expansion of n. Wait a minute. Why the hell would that make a difference? Why would it make a difference if I use n in binary versus if I use n in any other base? The following can be done on your calculator. It's a small enough calculation, we can do it directly. I want 3 to the 11th mod 7. Now, most of the time, I'm not dealing with 1 or 2 or 3 digit numbers. I'm dealing with 10, 12, 15 digit numbers. I'm dealing with the modulus being 6, 7, 8 digits long. I'm not dealing with numbers that are this small, but the idea is the same. If I asked you to take 3 to the 11th, divide by 7, and tell me what the remainder was, you could do that on your calculator. I'm going to use this. The reason I switch to binary for the exponent is because then I can do something you told me was more efficient. I can take powers by repeatedly squaring. And you told me x to the 2 to the k was easier if I squared repeatedly than if I did each of the multiplications directly. So I'm going to try and shortcut this by breaking this number up into how many squares it involves. Expansions in 2s, let's do it in binary. What is 11 in binary? 0. Now, if I think of these as powers, that's 1's digit, 2's, 4's, and 8's. Those are repeated squarings. Because that's what that binary expansion says, that 3 to the 11th is really 3 to the 8th plus 2 plus 1. Well, adding in a power is the same as repeatedly multiplying. So really, I only need to square again, and square a third time, and I'm all the way up to 3 to the 8th. Last time I checked, 3 to the 1st was just 3. Divide by 7, give me the remainder. You get 3. Square that. Mod 7. right? Because 9 is 1/7 with 2 left over. I want 3 to the 4th mod 7. I'm going to square it again. Now you say, well, okay, 9 squared is. I don't need to do 9 squared because I only care about the remainders. One of the properties of mods is when you're multiplying, you do the mod first, then multiply, and then take the mod again. So instead of doing 9 squared, I'm going to do 2 squared because I'm working mod 7. And that's why I put a congruence here rather than an equal sign. Now, 9 is small enough. What's 9 squared? Which is 7 times 11 with 4 left over. What's 81 squared? I don't know. But I do know that mod 7, it's the same as 4 squared. Now, I can actually do this. 4 squared is, which is 2 7s with 2 left over. So if I'm working mod 7, instead of doing this calculation, by the way, 3 to the 8th is like 6,561. I don't know how many 7s with how many leftovers. I don't care. Much easier to multiply 4 times 4, wasn't it? Now I can do this calculation right here. And if I do it mod 7, that's the same as doing 3 to the 8th mod 7 times 3 squared mod 7 times 3 to the 1st mod 7. And then doing mod 7 on the answer. Instead of just doing the mod once, you do it 4 times. But I know these numbers. We just worked them out. 3 to the 8th was 2. 3 squared was also 2. 3 to the 1st was just 3. Two times 3. Mod 7. Now I said this one was small enough I could actually do it on my calculator. Grab your calculators. What's 3 to the 11th power? Wow.
It's like 177.
177?
Yes.
Okay. Divide by 7 and give me the remainder. What's the quotient? You can give me that too, right? You're dividing by 7. How many 7s with what left over?
There's even multiply by 25306. I didn't get that far yet.
So take 177147 minus this product. This is 5, we have a problem. I never had to work out the number. This is particularly useful if my goal is only to get the remainder. Grab your calculators. What's 3 to the 43rd?
Um,
10 to the 21st, 10 to the 20th? That's huge, right? Now, your calculator has a finite memory bank. It only remembers a certain number of digits. After that, it just drops them all off. This is not a double or quadruple precision calculator. What's the last digit of 3 to the 43rd? I have the foggiest idea. I could probably write a simple JavaScript to tell me what this is, but that's the algorithm we're doing. If I do both steps at the same time, keeping track of what my resulting power from repeated squaring is and what I get from multiplying the last two together if I need to, I could actually do all of this in one fell swoop. Take a look on page 268. Now let's consider what this algorithm does. It starts with the number 1, x equals 1. It turns our exponent, n, into a binary representation. So all of those a's are either 1 or 0. You only need the thing when it's a 1. If it's a 0, don't change anything. So I'm going to take b, my base, and I'm going to raise it to the first power, b mod n. That's, in our case, 3 to the first. And then if this number is a 1, multiply this x by that number. That's this step where we're multiplying the pieces together. If it's a 0, don't. And then square the power so we know what the new power is. So we did 3 to the first. If that first number is a 1, multiply. If it's not, don't. But then you need 3 squared. So multiply the power by the power. But I'm doing it mod whatever, right? This keeps track of both numbers at the same time. It keeps track of what my multiplied power should be, and it keeps track of the value as we build the number from right to left. Gee, that's a familiar sounding way of storing a number, isn't it? Storing a number from the 1's digit up, like the algorithm on the exam. That's why you'll look here, it's A0, A1 from the right, not from the left. All right. With this in mind, I want to do this problem this way. So you should open your books to page 268 and see if you can write out the first 3 traces of this algorithm. While you are doing that, have your homework out on your desk so I come around and pick it up as I drop off these others down. I need the binary representation of 43. It's 43 in binary. A 32, no 16s, an 8 of 4. Wait a minute. If it's 32, then I should have 6 bits here.
101011.
Aha. A 32, an 8, a 2, and a 1. Now this is A0, A1, all the way up to A5. So this is where we start. And now we read our loop. If AI is 1, if A0 is 1, so what do? I take x times the power and I replace it. I take power times power and replace that once I mod 7 on both of these calculations. Have I reached the last number yet? Going right to left here? Nope. Loop again. A1 is a 1, yes? Perfect. Multiply this by that. And then square power. A2. Is A2 equal to 1? A2 is 0. I don't change x. But I do change power. Four squared mod 7. A3. Is A3 a 1? Great. I multiply these two. Six times 2 is 12. 12 mod 7 is 5. And I square power. I noticed something really nice. I'm going to keep bouncing back between 2 and 4 here, aren't I? That's convenient. This problem is rigged. A4. What's A4? That means I don't change x, but I do square power. What's A5? So I do multiply. Five times 2, mod 7 is 3. Technically, I should also do this. But since I am now done, I've reached the end of my number, I can now spit out the answer. The answer is 3. How far?
Well, right there, it's fine, but with the power, how are you determining what the base is?
It's always the last number. It's whatever was in power squared. As a matter of fact, if we look at the algorithm itself, that's what the algorithm says. It says power. The new value of power is the old value in power squared. Power times power. Now, for all you know, I'm blowing smoke up your ass. So how can I check this? This number is 10 to the 20th. It's too big for my calculator. Well, it's too big for the calculator in my hand. I need a bigger calculator. On our Canvas page, under the web links section, at the bottom are two different calculators. Web 2.0 scientific calculator and a big integer calculator. That calculator only does whole integer math, but it does octuple precision integers. It can do numbers that are hundreds or even thousands of digits long. So if you actually want to do this calculation, I'd recommend going there. 3 raised to the 43rd, right? X raised to the Y. Push the button. There's our 21-digit number. I just realized this is not going off on the recording. Let me actually share this into the Zoom so we can see it there. Now I want to take that answer, put it up there as one of the numbers. So I'm going to take the answer and stick it in the X spot. And then I'm going to replace Y with 7. And I'm going to say X mod Y. There's my mod button. It worked. There's another way I could check this. And that's doing the same calculation that we did up here. Because we said here, 11 was an 8, a 2, and a 1. Down here, we know 43 is a 32, an 8, a 2, and a 1. So I could take 3 to the 1, 3 to the 2, 3 to the 8th, and 3 to the 32nd, which I worked out here, and multiply those together. I would love to tell you this is worthless garbage. This is the backbone of the RSA cipher. This is the start of knapsack public key encryption. Yes.
So for the answer, we would just have 3, we wouldn't have the power anymore.
No, the answer is X. I don't need this one power. I don't get to use it, but it's in the loop, so I don't not do it.
You just needed it for the multiplication of the X later, right?
Yeah, each power got used when I ran into a 1, I multiplied by the power on the previous line.
Gotcha.
So technically, right here, I should have said, oh, that's a 1, so take the X from the previous line, multiply by the power from the previous line.
I think it's just because it was always 2, I just kind of didn't see the connection there.
Oh, no, it's whatever power has the previous from the previous line. More questions? In order to understand encryption better, I need to make the numbers I am working with hard to figure out. So I need to know some more things about the exponents I'm using, about the moduli I'm using, about the bases involved. And one of the nice things, one of the largest pieces of information we want to know about numbers is whether or not they are prime. A number is prime if it has exactly two positive integer divisors. Another way to say this A and P are both positive integers. P is a prime integer if and only if, where A is a positive integer, P is a positive integer, A is either 1 or P if it divides P. Please notice, these two are different definitions. It's a very subtle difference, but there is a difference. And it's a question that we argue over a lot in math. What is the smallest positive prime number? The only things that divide 2 are 1 and 2. What about 1? According to that first definition, no. The only positive integer divisor of 1 is 1. It only has one of them, doesn't do it. But according to the second division, 1 divides 1, that's true. But there's no other number that does it. We fall into this first definition far more often. 1 is not prime. I promise there's another reason for that. We'll discuss it more later. Question?
Is that supposed to be?
No, that's an OR. If A divides P, then A is 1 or A is P. If a number divides 2, it's either 1 or 2. If a number divides 7, it's either 1 or 7. What about 6? Oh, wait a minute. 2 divides 6. 2 is not 1. 2 is not 6. A number that is not prime is called composite. There are lots and lots and lots of prime numbers. These numbers are all prime. 2, 3, 5, 7, 11, 13, 23, 29, 31, 37, 41, 43, 61, 89, 5,119, 9,973. 2 to the 110, 503 power, minus 1. Otherwise, it would be divisible by 2. 3,610 factorial, minus 1. Okay, for the record, this one is 33,000 digits long. This one is 11,000 digits long. Those are small prime numbers. I turned on Save Search on purpose. Google the word GIMPs. You get the great internet Mersenne prime search. Mersenne primes are of a specific form. They are 2 raised to a prime number minus 1. Like our 2 to the 110,503. October last year, a computer search turned up 2 to the 136,279,841 minus 1. This number is 41 million digits long. And we're not done yet. Finding prime numbers is not just a mathematical challenge. In previous mathematical history, number theory and the study of prime numbers goes all the way back to Greco-Roman arithmetic. And understanding how numbers worked was one of the foundations of number theory, which was nicknamed, by the way, the Queen of Mathematics. Turns out the reason I don't want to use 1 as a prime number is this result, the fundamental theorem of arithmetic, which says that every integer bigger than 1 can be written uniquely as a product of primes, with factors ordered by size, allowing for repetition. So I would say to you, oh, somebody pick a number. 10. 10 is 2 times 5. That's the only decomposition of 10 in primes, going from small to large as we go from left to right. 51 is 3 times 17. 17 is prime, 3 is prime. 1,999,877 is 11 times 281 times 647. And all 3 of those numbers are prime. 999 itself is 3 times 3 times 3 times 37. And all of those numbers are prime. If I allowed 1 as a prime number, then none of these would be unique, because I could keep multiplying by as many 1s as I wanted. So there's the reason I don't want to think of 1 as a prime number. It F's up my unique decomposition. By the way, it is possible that your number itself may already be prime, in which case you have a product decomposition that is just that number. Questions? Proving unique factorization, the proof of the fundamental theorem of arithmetic, is about 6 pages more math than I think we can do in this course. I will happily go through that proof for you in abstract algebra SMA205. But it requires us to learn something about the structure of the numbers underneath the numbers themselves, called the ring theory. I will happily discuss that during office hours. Come bug me, I'll walk through this proof with you. On the other hand, bring aspirin. Or take a lot more math between now and then. This was conjectured by Archimedes and Euclid and a bunch of Greek mathematicians, but the actual formal proof Took quite a while. It was only really written out correctly in the 17th and 18th and 19th centuries. More questions? All right. How do I find these numbers? Oh, crap. Wait a minute. Here's a claim. I wrote it as a theorem, so I should be able to prove this. If my number is composite just means not prime, then it's got some prime divisor. And that prime is less than or equal to the square root of n. Why? My number has a factor. It's composite, right? This proof is actually shorter than you think it is. If my number was prime, then the only things that would divide it are 1 and itself. Since it's not prime, it's got to have two other numbers. So when I multiply them together, and those numbers can't be 1 and they can't be the number itself. They got to be in the middle somewhere. Well, wait a minute. I claim one of those numbers at least. Either A or B must be smaller than the square root of n. Now, Emily, I saw you nodding, but that's a question. That's a statement that needs some justifying. Why do I know that's true?
Prime factor.
I haven't said anything about A or B being prime, have I?
For it to be composite, then one of them has to be a prime factor.
I haven't said that. 32 is 4 times 8. Neither 4 nor 8 are prime.
Because if A is equal to B, then they're both just the square root of n. But say A is larger than B, then B is less than the square root of n.
If they were both bigger than the square root of n, then when I multiplied them together, I get something bigger than n, wouldn't I? That's a contradiction. So that one of them has to be smaller. Now here's the statement. One of them, I don't know which one. Without loss of generality, pick one. Without loss of generality, assume A or B, flip a coin. A is less than or equal to the square root of n. One of two things is true. Either A is prime or A is composite. But what do I do if A is composite?
down even farther.
Do it again. What has to happen? Every time I take a square root, I make the number smaller. Eventually, I have to get to a number that's prime. Or I would get to 1, and neither A nor B can be 1. And I might take 2 or 3 or 4 or more loops through this process. Emily, I was particularly vicious when I say, hey, 32 is 4 and 8, but neither of those are prime. Okay, take 4 and make it smaller still, and lo and behold, I get a 2, and that's prime. And since 4 is already smaller than the square root of 32, and 2 is smaller than it, I must be getting smaller still. But this also guarantees me a way to find out whether or not a number is prime. Here's a number. Is this prime? This is when having the right library helps, because I could just write is prime 103 and be done. But what's that algorithm do?
Iterate until the number is 1.
Iterate what?
In the previous proof, we kept taking out the factors. So we found a prime one. If we didn't find a prime one, we got to 1, that means it's prime.
Yes, that's one way to do it, but I think I'm going to do it the other way. I'm going to start with the small primes and work my way up. And as long as I don't find a prime before the square root of 103, I know I'll be done. What's square root of 103? Actually, I want the integer floor of the square root of 103. Square root of 103 is a little bit bigger than 10. So the integer floor will be 10. Well, wait a minute. All I need to know now are the prime numbers less than 10. That's it. Those are all the primes. So now I can ask the question. Does 2 evenly go into 103? How do you know? Remainder is 1. What's the remainder when I divide 103 by 3? The remainder is also 1. Divide 103 by 5, the remainder is 3. Divide 103 by 7. As long as you have decimals after your number, you know it's not an even multiple. 2 does not go evenly into 103. 103 mod 2 equals 1. 3 does not evenly go into 103. 103 mod 3 is also 1. 5 does not evenly go into 103. What was 103 mod 7? What were the decimals after the number? 7, 1, that's 5. The remainder is 5. 5/7 is 0.714. 6/7 is 0.857. All you have to do is know your sevens. Although I will tell you that I'm cheating. I used to grade a lot of papers out of 7, so I have those numbers memorized. There we go. Hey, wait a minute. The next prime number is bigger than the square root of 103. Stop. If your number is composite, then it must have a prime factor less than the square root of n. We don't. Contrapositive, this number must be prime. Now I'm going to iterate my idea. I'm going to give you a big number. Well, a little big. And I'm going to ask you the same question. Is this prime or not? Now I'm going to be a moist robot and follow the algorithm. I need all of the primes up to the square root of 7,007. If I'm lucky, I'll find a small prime. If I'm not lucky, I might have to go a ways. What is the square root of 7,007? It would help if I had a list of a bunch of prime numbers, wouldn't it? Page 274. Shows a list of the prime numbers under 100. Right here. Right above the break paragraph here at the bottom of page 274. So I have a list. I need all the prime numbers up to 83. Let's start dividing. What's 7,007 divided by 2? Well, what's the remainder? 1. 7,007 divided by 3. The remainder is 2, because it ends 0.666, okay? How about 5? Because it's got a remainder of 2. How about 7? Ta-da! Well, now I can repeat the process on 1,001. And since neither 2 nor 3 nor 5 worked, I don't have to check them again. I can start my loop from 7. What is the floor of the square root of 1,001? So I only have to go up to 31 now. I don't have to go up to 83. I've even made the set of numbers I have to look at smaller. And I can start at 7. Because it could be that 7 works again. Does 7 divide 1,001? Lo and behold, it does. 1,001 is 7 times 143, which means 7,007 is 7 squared times 143. What's square root of 143 rounded down? Which means I only have to check the numbers from 7 to 11 that are prime. Well, that's just 7 and 11. Does 7 divide evenly into 143? (143) divided by 7 is 20, with 3 left over. Then the next number is 11. 143 divided by 11 is and that means that 7,007 is 7 squared times 11 times 13. There's my prime decomposition. How do I get the list of primes? That list on page, whatever the hell it was, 274, where did it come from? That's what we will discuss. on Wednesday. I will see you all then. Hope you have a wonderful rest of your day. If you have more questions about the exam, please come talk to me. If you haven't given me your homework, if I didn't get it from you when I passed out stuff, please bring it up. See you all on Wednesday.